We'll go ahead and get started. This is going to be the last half of last lecture because we didn't get to it because we were all sitting and talking about how awful assignment 1 was and how maybe it could be less awful in the future. But we wanted to talk about other join algorithms besides nested loops because nested loops is awesome because it's general and we want to keep a general purpose join algorithm around for those crazy cases where people do non-equijoins and other like joins on functions or whatever we might have that we can't handle with any of these other more sophisticated ways of joining. So nested loops is nice to keep, but since most of the time we're doing joins on inequalities, it would be nice to have join algorithms that are optimized to do these joins fast. So we had just begun to talk about this last time. There's two other general families of join algorithms, and they are typically a lot faster than nested loop join, which is why most of the time databases choose to use these join algorithms instead, except for MySQL, which can't do them. So, things like Oracle, Postgres leverages these other join algorithms heavily. First one, sort merge join. This is a situation where we can use ordered inputs to do our joins more efficiently. Obviously, it needs to be ordered on the join attributes. And in this situation, R and S are being joined, and we're joining on column A. Let's just pretend we're doing a natural join. And you can see that the tuples are ordered on A. And so we have, they're definitely ordered just on A because we have 15 pig, 15 frog. That's not in total order, but it's just ordered on A. So what we do is we have two positions in the input relations or the input tables. And anytime we have this pair of tuples that we're considering, we just figure out if the join attributes are the same, and if they are, we can generate join results. Otherwise, we have to move some pointer forward. Like it says here, if the left relations values for the join attributes are smaller, we move the left pointer forward. Or if we're thinking about it, we could say, the left relations values don't match, and we're doing a left outer join, so I could generate a tuple from the left tuple. I could do something like that. If the right relations values for the join attributes are smaller, we move the right pointer forward. Otherwise, we go ahead and join the runs of tuples that we have with equal values. Really straightforward. There's not really a lot of complexity to this, except that we'll discover that there's a bit of a wrinkle here. Because you'll notice that we do have runs of tuples. How many tuples should we produce with A equals 11? 2, right? That should be pretty easy to do. We should have 11 dog pink, 11 horse pink, right? That should be the results of joining the rows 11. But let's say that we have the pointers are on rows with A equals 15. How many rows should we generate this time? 4, right? And this is where it's a little bit challenging because we should get 15 pig blue, 15 pig red, 15 frog blue, and 15 frog red. So we should generate these results. And so we have a situation where, remember, we keep asking for the next tuple. I keep saying to R, give me the next tuple, give me the next tuple, or that subplan, and with S, for that subplan or that table, give me the next tuple, give me the next tuple. And this is a situation where we need to be able to roll back to an earlier point in the tuple stream to, traverse a sequence of tuples again. So, like I have here, let's say that you do 15 pig and you say, okay, 15 pig, 15 blue, those match, I'm generating a result. And then you say 15 pig, 15 red, that matches, so I'm going to go ahead and generate a result. And then you go ahead and move it forward to 19 mauve, and you're like, oh, okay, I have a problem here. So what you'd like to do is advance the left guy. And so you advance the left guy and say, oh, it's 15 frog. Well, I need to roll back to the point where, or I should say reset back to the point where I had my rows with 15 again. So I have situations like that where I need to be able to mark a point in a tuple stream and then reset back to that mark and redo those rows. So what we do is we incorporate the ability for plan nodes to be able to mark a particular point in a tuple stream and then go back to it. Does every tuple, or does every plan node support this marking thing? No. Not every single kind of plan node is able to support marking efficiently. And so we don't want to support marking everywhere. I think like nested loop join, I said, forget about it. I don't want to try to support marking on nested loop join. You could probably incorporate it if you wanted to, but there's easier ways to do it. And so there's no point in trying to support marking on every possible kind of plan node. The alternative, of course, is as you're traversing these things, you try to store these things in memory. You cache them in memory. But you can't guarantee. I mean, what if you had a situation where S was 1 billion records and every one of S's rows had 15 as the value? Well, then you're starting to run into some challenges. So the easy way to deal with this problem is to just support marking and resetting to a particular marker point in the plan nodes, and then it becomes easy to handle this kind of situation. Now remember, we already talked about materialized evaluation, and we can actually apply this in a small set of cases by providing a way of materializing the results of a particular plan node. Like I say here, not every kind of plan node can provide marking, and not every kind of plan node can be reset to the beginning of its tuple stream. Imagine a situation where you're consuming them off a network connection or something like that. It would be very difficult to say to the thing that's sending the results, hey, reset back to where you were and let's go through it again. So in those situations, we can insert this special kind of plan node called a materialized plan node. And what that materialized plan node does is it just stores up the values that it receives. And what it frequently does, what these implementations frequently do, is they will accumulate results in memory until it takes a certain amount of space, and then they'll start using the disk. So for example, I will consume up to 100 kilobytes, and then I will start writing stuff to disk because I don't want to consume too much memory. This is a very common technique in database systems to allow you to do marking and resetting, or to evaluate and then cache results so that you can traverse them multiple times efficiently. So that's called a materialized plan node. And it's materialized evaluation, but only in certain points in your plan. You can choose where you insert these materialized nodes so that you don't have to do materialized evaluation for everything. Now, another situation where materialized evaluation can be very helpful is if you have a nested loop join that you can't avoid, and the right subplan happens to be more complicated than just a table. Because remember, if I have a table, I can go ahead and cache the whole thing in memory, and it's really easy to go back to the beginning of the table. I just seek to that point on the disk and start scanning again. But if I have a situation where I have some complicated subplan on the right, then I don't want to deal with this. Because remember, this, like if that top theta join was being implemented as a nested loop join, then I scan through the left subplan once, and I scan through the right subplan once per tuple in the left subplan. And that's kind of crazy. I don't want to do that. So instead what I do is I insert a materialized node, and then I only have to evaluate the right subplan once, and I cache it to disk, or if it fits entirely in memory, I can go ahead and fit it entirely in memory, and just scan it in memory, and then everybody's happy. But these materialized plan nodes can often be very helpful in allowing us to have more optimal evaluation of plans that have certain structures. Yes, question? Is it inefficient? It is less inefficient than evaluating the right subplan a bunch of times. That's the idea. Okay, remember, we have situations where, let's say that T3 and T4 were large tables. Think about it this way. T3 and T4 are very large tables, and only a small number of rows are generated by joining them together. So I'd like to cache that small number of rows that are joined together and scan those a bunch of times rather than scanning through these large tables a bunch of times to do the join over and over and over again. That's the idea. Why would we not want to do that? Well, that's certainly true. I mean, it may be that we can restructure this in some way to make it more efficient in general. In fact, when we start talking about planners, one constraint that planners frequently constrain themselves to is to only create left deep join plans, which basically means all the joins are in the left subplan always. And on the right subplan, you'll have simpler stuff. Grouping and aggregation, maybe, situations like that. But you generally, I should say, many planner optimizers constrain themselves to only generate left deep subplans. It gives them a lot less a lot less plans to consider in the planning and optimization phase. So you could certainly do something like that. But there are situations where you can't avoid it. And having the ability to materialize results temporarily to make plan evaluation faster can be a very, very helpful technique. Okay, so anyway, enough about that. We'll go ahead and go on. Here's an example of how to implement sort, merge, join in a plan node. This is actually stolen from Postgres, so you can go look at node merge join.c if you want in Postgres, and you will see this implementation or something like it. This is sort of a high-level description of it. So you start with the left tuple and right tuple being the initial left and right tuples from the left and right subplans. And then you have this first section here. Well, the left tuple is not equal to the right tuple. You know that you're not going to join, so now you have to figure out which subplan pointer you need to advance. So like it says here, if the left tuple is less than the right tuple, and of course this is using the join attributes to figure out which one is less, then you advance the left subplan, otherwise you advance the right subplan. And so you can imagine it advances the left subplan's tuples for a while because those are less, and then maybe it switches to the right subplan because suddenly it's less, but they still haven't gotten equal. This loop will execute until the left tuple and the right tuple would join. So we have that occur, and it says, like it says here in the comment, now left and right tuples have the same values. So we mark the right subplan's position because we may need to come back to it if we have multiple tuples on the left that match. So the mark value is the right tuple. And then we say, while the left tuple is equal to the right tuple, add the joining tuples to the result and advance the right subplan. So I'm keeping the left one fixed, and I'm advancing through the right tuples that match. And I'm generating a output row, output row, output row. Suddenly they don't match anymore, and I need to go back to the marked point and advance the left tuple. So he says here, advance the left subplan. If the left tuple is still the same as the mark value, then I can reset back to that mark and join the next. I can join that run of tuples on the right side with the next row from the left tuple or the left subplan that matches. Now, if it doesn't match, then I can go ahead and I don't need to mark because I've finished joining that run, and I can go ahead and go back to the top of my outer loop, which you can see while true, and I go ahead and scan again until I find pairs of tuples that might match. And then I go ahead and generate my runs of matched tuples. Does that make sense, everybody? Yeah.
So how do you break out of the outer loop?
How do you break out of the outer loop? When left tuple and right tuple are both null, you could break out of the outer loop. Or if you're doing an inner join, you could just break out when either one is null. You could do something like that. Yes, that's a good point. I don't think I actually have any specific code in here to break out of it. So yeah, so this is what you could do if you wanted to alter this to the way NanoDB does things, is to just go ahead and say, like, while left tuple is not null and right tuple is not null. You could do something like that. Yeah?
Looking at the code, it seems that NanoDB wants to, rather than do a while true loop, it just has an iterator. So
Yes.
in that case, would we just kind of say, like, something is done and then check that, and then rather than advancing something, you just like take the next two whichever plan you want to take it from?
Well, that's an interesting question. How would you implement this in NanoDB? And that is the challenge that you generally have. And this is what you'll have to deal with this week in implementing nested loop join, because nested loop, the way that I pose the algorithm, is one where it generates the entire result in one shot. And this is where I mentioned to a few of you, Python would be really nice for implementing these plan nodes because you could just have it yield the joins result that it's supposed to output that time. And then you invoke the function again, and it would look till it generates the next tuple and yield it again. But the reason why I want you to go through this process in a language like Java, which doesn't have that mechanism, is I want you to see what it's like to implement these things in such languages, because this is what language, these are the ways that databases are normally implemented. So when you have something like this, again, this is implemented in a way that generates all the results at once. So you have to figure out how to take this and transform it into something that will generate results one at a time. So again, you'll probably have to have some kind of state, which I think you can do it by subclassing theta join. I will probably have that on a subsequent assignment to implement sort merge, so you can start thinking about that now. But I believe theta join already has a left tuple and a right tuple, and yeah, you can have a done flag and look at it and figure out, okay, what do I need to do? And you can see, for example, that the first innermost while loop, the while left tuple is not equal to right tuple. You would always have to do that every single time when the sort merge joins get next tuple thing was invoked. Because what we're doing is we're skipping over a whole bunch of tuples that don't join. That is if you're doing inner join. Once you get to the second part, now you're generating results that can be joined. And so you'd have to keep track of the state of what's actually going on so that you can call the function once, generate a result, return, but then the next time it's invoked, you can pick up where you left off. And so that's the interesting challenge of implementing these algorithms in a database, is being able to do that kind of thing where you invoke the function, it takes one more step and returns the result. So it's a little bit challenging, but that is part of the challenge of writing a database system in the languages that people typically write them in. So. Now, we're going to assume that the input relations are already sorted, because if they weren't, we'd have to sort them before we could use sort merge join. And as a historical note, it's kind of interesting that when nested loop join was the only real way that databases joined data, and then somebody figured out sort merge join and said, hey, let's start using this algorithm for database implementation, it was less expensive to sort the data and then run sort merge join. And so people did that. And not only that, but people would use these sequential file organizations and incur the cost of maintenance and so forth, because sort merge join was so much faster than nested loop join that it was worth the trouble of keeping the data in sorted order. So it's kind of funny that people started switching to sort merge join pretty quickly once people had figured out how to implement that in database systems. Okay, now the other thing that we're going to assume here, as far as costing this, is that the join attributes are a primary key in both input relations. And that's kind of important because it means that we can ignore runs of matching tuples on the right-hand side that we have to mark and then reset back to that mark and traverse again. Because if we have a situation where we're joining on something that's not a key, then we'd have to sort of figure out some way of estimating, well, how many times am I going to have to go back and traverse a chunk of tuples again? You'd have to start thinking about that kind of thing. So we're going to pretend that that doesn't exist. And so like it says here, for R join S, the result of evaluating that will be that you read all of R and then all of S once. So BR plus BS, that's how many blocks you're going to have to read. Now, how many large disk seeks are you going to have? Okay, we're not talking about just all disk seeks, because obviously that's probably a fixed number if you look at the size of R and S, because you have to traverse every sector. But how many large disk seeks are we going to have? If we can only hold one block of each of R and S. I'm sorry? Yeah, that may actually be true. I'm trying to think, because like as you're reading through R, okay, so you're in a block of R, and then you have to jump over and read a block of S, so that would be a large seek. And then you finish that block, you might have to read the next block of S, and that would be a small seek, or you might have to jump back and read another big block of R. So you can see that we could get into a situation where it's pretty bad. We're going to approximate this as just BR plus BS, just to keep it simple. That would be sort of the worst case. But you can see that we have a problem. If we can only hold one block of each of these tables, it doesn't do very well. We don't like it very much. So sort merge join is one of those algorithms that really benefits from buffering. And you really wouldn't want to use it if you don't have a lot of memory buffering that you could rely on to avoid these disk seeks. So like it says here, you allocate a certain amount of buffer blocks for each input relation, and you use read ahead so that you can just suck in a whole chunk of that file, and then that means that for reading that entire block, you're not going to have any disk seeks except for the seek to get to the first part. And so then you can go ahead and get to this kind of performance. He says here the BR divided by the number of buffer blocks that you can use for reading R, and BS divided by the number of buffer blocks you can use for reading S. And so that gives you a better seek performance. This is the one where it's kind of a big pain. What if all rows in R and S have the same join value? And this is like your absolute worst case, because remember you have to mark at the beginning of S, scan it all the way through, and then you advance R and you reset and you scan all of S again. Does that sound familiar? And then you advance R again and you reset S and scan it again. So basically we have a situation where it starts behaving just like nested loop join. So that's no fun at all. So sort merge join really likes to have buffer space so that we can make this a more performant algorithm. So yeah, same strategies to sort merge as you would have on nested loop. So like it says here, the table on the right should fit within memory if it's possible. And if it's not possible, you try to grab as much buffer space as you can to reduce the number of seeks. And like it says here, if the right subplan is more complicated than a table scan, then you would use a materialized node. This is, like if you look at Postgres's explain output, you frequently see if the right subplan is actually a subquery of some kind, that gets materialized all the time. It sorts it, then materializes it, and then it can go ahead and just treat it like an intermediate table, a derived table that it can just scan. Okay, yeah, and like it says here, our cost estimates are assuming that the inputs are sorted. Now, the reason why we can do that is because when we cost a whole plan, the sorting cost will be covered by the parts of the plan that actually involve sorting. So we can that's why we can go ahead and just focus on sort merge joins cost by itself. Okay, outer joins. Where would we do left outer joins? Well, where do we handle rows that don't match? Everybody see where we handle rows that don't match? It's in that first innermost while loop. So if we're handling situations where we're generating left outer joins, well, we have this while left tuple is not equal to right tuple. Somewhere in there, probably the very first thing we would do after we detect that they don't match is generate pad nulls left tup and add that to the result. What if we're doing right outer join? Do we need to flip the inputs like we did with nested loop? Why not is certainly an option. But we don't actually have to do that here. Because, again, the left tuple and right tuple don't match. So if we're doing right outer join, well, we could just do pad nulls right tuple and add that to the result. So we could do that as well. What about full outer join? Same thing. We can do full outer join with this very easily. We can detect when the left, anytime that you can add left outer join and right outer join easily, you know you can do full outer join easily. So just the same thing. We would just go ahead and generate an output for the left tuple. Well, basically, now you'd have to do it inside the if. So you generate a result for the left tuple, and actually you'd probably have to do that with the other outer joins as well. Do it inside the if block. Makes it easy to generate the results for the outer joins. Anyway, very easy to take this and customize it for generating outer joins. In fact, the one algorithm that's the best at generating full outer joins is sort merge. So if you need to support full outer joins, the really easy, helpful way of doing it is by implementing a sort merge join, and then it's very easy to generate full outer joins. Okay, any questions? You can keep that in mind. I really want you guys to be able to implement sort merge join this year, and maybe we can have NanoDB doing full outer joins. That would be really cool. Now the other kind of join that we care about is hash joins. And this works basically as you would expect. You hash on the join attributes, but we use kind of a clever technique because, again, R and S may be too large to fit in memory, and so we need to figure out how we can actually deal with these input relations that may be too large. So like it says here, for R join S, we're performing the equijoin on some set of attributes. We'll call them the join adders. And what we do is we apply a hash function. You can see that we call it H sub P. The P stands for partition. So this is a partitioning hash, and we take it and we apply it to R, dash R into some number of partitions, and we also hash S using the same hash function into some number of partitions as well. You can see that it will generate the same number of partitions. Now when we're doing this hash join, what do we know about, let's say, HR0 and HS2? What would be the join of the tuples in HR0 and HS2? Remember, we're hashing on the join attributes. Yeah, basically, HR0 will only join with tuples in HS0. HR1 will only hash with tuples in HS1. So what we're doing is we're taking a large hash join problem and we're decomposing it into a whole bunch of small ones. Makes our life much easier. So that's pretty nice. This is why hash join is so nice, because basically you're building a hash index on the relations, and this is why hash join is so good in dealing with joins against derived relations. You don't have an index on the derived relation that you can leverage, so hash join builds it on the fly. So once we have these things partitioned, so there's two phases of this. You have the partitioning phase, which goes first, and then you basically join these pairs of partitions in sequence. And so now you have two more phases. You have a build phase, where notice you load the right partition, HSI, into memory, and you build another hash index against it using a different hash function. You can't use H sub P again because, well, that gave us the partition. That would not give us any new benefit. So we have to use a different hash function. And you can see that that's going to help us to generate an index in memory for this partition HSI. So that's the build phase. And then after that, we have the probe phase, where we basically run through each tuple in HRI, and we probe this hash index to figure out what tuples in HSI match that tuple that we're considering in HRI. And you'll notice that the only constraint that we really have here is that the partition HSI has to fit in memory, including the in-memory hash index that we built. We don't even have to store HRI in memory because we're just scanning through it tuple by tuple. So we have to be careful in how we build these partitions so that we can make sure that each partition on the right fits into memory. Now I have some pictures of this. Yeah, so S is called the build relation. Hopefully you can see why, because remember, as we partition it and then load each partition, we build an index on the right partition. So that's why we call it the build relation. So we go ahead and load in HSI. We build a hash index on it by traversing the tuples in HSI as we load it in. That's no big deal. And then R is called the probe relation. Again, hopefully that's obvious why it's called the probe relation, because as we scan each partition, we probe the hash index we built to see what tuples match each tuple on the left. And it's just really nice that HRI don't have to fit into memory. It's only the HSI that have to fit into memory. So we load a tuple, and we use it to hit the hash index and see what pops out. Okay? Hopefully, another thing that you can see from this is like, well, how would I implement left outer join? Well, when I use that probe tuple to hit the hash index, if nothing comes out, I know this is a left outer join result. I got to pad nulls and send it out the door. Now what if I'm doing a left anti-join? Same thing. If you can do left outer join, you can do left anti-join easily. So you hit the hash index, nothing pops out. You're like, okay, R is my tuple. I'm sending it out the door. If I hit the hash index and anything comes out, then I know it's not in the anti-join result, so I can pop it out the door. So again, when you're looking at the way that Oracle or other databases do not exist type queries, not in type queries, you will typically see them say hash anti-join in the explain plan, because it's using a hash a hash join in the mode that it's doing an anti-join to evaluate that query. Okay? So yeah, like it says here, generally the smaller relation should be the build relation, because that's the one that you have to fit the partitions into memory. So that, you know, if you keep the smaller relation on the right, then it will reduce your memory usage requirements. Because HRI you can just scan through. And if you have a large, again, think about how this works. You start loading HSI, so you have a disk seek to get to the beginning of HSI, then you scan through it when you're loading it, then you big seek to get to the beginning of HRI, start reading it. If HRI is huge, we don't mind, because we only have one seek at the beginning of it, and then we have a whole bunch of small seeks. Okay, so partitioning, you can see, does require a complete pass over both R and S. And so, like I say, it requires 2 times the quantity BR plus BS disk transfers. Now, you can do this basically in sequence. Yeah, this is just an implementation detail. Basically, your last partition can end up being only partially full, just because you have to deal with the fact that you may not divide it evenly. Join process itself reads each partition once. So again, you read each, and of course there's change here. I don't know if I remember. Yeah. So, but basically, this is going to be the number of reads that you have to do for hash index. I should really say reads and writes, because you have to write the partitions out too. Okay, so the number of blocks in R plus the number of blocks in S, multiply that by 3, because I have to read everything in, write the partitions out, and then read the partitions in. That's basically what you've got. Okay? Does that make sense? Yeah.
So we're not considering like the processing cost of hashing?
No, we generally don't consider CPU cost in these things, because CPU cost is like a millionth of the cost of disk access. So generally, we try to optimize on disk access. Now, when real people write real databases, unlike our CS122 toy database, they do think about CPU cost. They try to think very carefully about that kind of stuff because, for example, the less memory they use, the more concurrent queries they can run, or the less disk seeks they need because they can load more data into memory. And the more efficiently they use the CPU, it's like everybody cares about the constants when you're trying to optimize a product for commercial use and so forth. But as far as disk access, that so trumps CPU usage that we just don't care. Like, as a first approximation, it is totally fine to just focus on disk access. And you'll actually see this. You'll notice this once you have nested loop join working in assignment 2. There is I think it's called stores, but there's a special schema in the schemas directory that's stores, and there's like 3 tables or something like that. And you can actually do some joins across those different tables once you have nested loop working and you have a planner that works. And since we don't have an intelligent planner, it just naively translates the order of the joins that you give it, and if you use an on clause, it'll put the predicate on the theta join, or if you use subqueries, and it'll put the theta join, or it'll put the predicate on the select, or you can put the predicate on the top level select. Try different orders. See how it affects the time it takes to compute things. And you can have a query that'll take like 1.5 minutes to run, or it'll take half a second to run, just by how you order things. And it really comes down to disk access. It also has to do with how many tuples you generate in different parts of your plans. But it's interesting that disk access has such a profound impact. So that's just an aside. You'll encounter this soon enough when we get into the third and fourth assignments where we actually do more plan costing and try to come up with an optimal plan. But yeah, this is why we just really focus on disk access. Okay. Yeah, so the biggest issue, like I say here, is if the partition HSI doesn't fit entirely into memory, because then we have a well, okay, so we build, and then, yeah, so when you have that hash index, the reason why this matters, let me go back to this picture, is that you have this HSI in memory, and that hash index doesn't actually hold the tuples in HSI, because why would you do that? What it'll do is it'll have things like page tuple structures, you know, the equivalent in whatever implementation you're using of our page tuple structure, which will be like, here's the page number and here's the offset in the page, go give me that tuple. So that you have the tuple data loaded into a buffer, and then the hash index just says what tuple, where it is to go get it. So that's important to keep in mind. If HSI doesn't fit entirely in memory, now when you try to access stuff, you're turning around and hitting the disk some more. And you're going to start generating seeks and you're going to start generating reads because HSI doesn't fit entirely in memory. So that's why it's a big deal if HSI doesn't fit into memory. And sometimes this is something we can't avoid because, like I say here, it may be that our join attributes don't have a good distribution in some of our input tables. So this is another aspect of what planners have to think about. If I'm doing a hash join, does my data actually have a distribution that is friendly to that approach? So there's a couple of different possibilities. One is overflow resolution. So I detect that I have an overflow. And you can do this during the partitioning phase. I'm generating partitions and I discovered a partition that doesn't work for me. So I need to hash it again and try to break it down into smaller partitions. Another one is to go ahead and generate a whole bunch of tiny partitions right off the bat, because then I can just consume as many partitions as I can to fill up memory. I kind of prefer overflow avoidance because it's kind of more fun to me, but you'd be generating a bunch of small files on your disk, so that is the one downside of that. Okay? So probably overflow resolution would be the most efficient approach, but overflow avoidance is kind of appealing to me, just because I like that kind of approach. Yeah, question, comment?
Yeah, because you mentioned data like hash stuff, in general, what kind of hashes do you use?
So these are pretty generalized hash functions that we're talking about here. And when we talk about H sub p and then H sub I, so we're talking about the partitioning hash function and the indexing hash function, they're not that complicated, they're not that sophisticated. Really what we do is we have some hash function h that we apply to the data, and then H sub p is just h modded by something, and then H sub I will be h modded by something else. And so that's why you have to be careful, because if you don't take care to avoid issues with that, then your H sub I could end up not hashing your data very well. So that's kind of the approach there. So it's a little bit tricky. And everybody I think is familiar with string hashing, and like if you're hashing an integer, well, you could either just use the integer. There's various techniques if you have a long and you want to try to hash it into an integer value or something like that. So various techniques that you can use. But yeah, these hash functions tend to not be very sophisticated because they have to be generalized. They have to be useful for whatever data you might be storing. And I suppose that one could spend some time thinking about that and being a little bit clever and get a lot of benefit out of it. It might allow you to use hash joins in a lot more situations. Okay, yeah, and so like I say here, a good planner will look at the data distribution and say, oh, I'm joining on a column with 5 different values. It doesn't really make sense to use a hash join because my partitions will all be huge, and when I actually do my indexing hashing, then that's not going to benefit very much either. So it would just discard hash join as an option in those situations. If you decide to be this clever in NanoDB, then that will be on your own, because I don't really require this for any assignment to implement hash join or anything like that. It's sort of a step too far for the current incarnation of NanoDB. Okay, any other questions? Okay, yeah, so let me see. Yeah, so this is the same thing that I mentioned when I was talking about doing external memory sorting. If you have a situation where the number of partitions required, because remember that as you're scanning through R, you're building all these partitions at once. And so you have to have a way of generating all the partitions at once. What this really means is I need to be able to have one block of each partition file in memory so that I can put the tuple into each partition file's block as I'm generating it. And then when that block fills up, I push it out the door, and I create a new block, and I start filling that block. So I might have a situation where I have so many partitions that I don't have any way of storing one block of each partition in memory. And we do the same thing that we had with our external memory sort. I hash into some number of partitions that actually fits in the memory, and then each one of those I then recursively hash again. And I do this over and over again until I end up with every hash partition actually fitting into memory. Or like I say here, it's really the right one that we care about, because the left partition we don't need to load entirely into memory, but the build relations partitions we need to be able to load. And I say it's generally not required until tables are many gigabytes in size. That was probably from the first generation of this slide, because by now, with memory sizes and so forth, you could probably get up into many terabytes before you really ran into this problem. So gigabytes is not really a big deal anymore. Okay? Let's see, what's next? Yeah, so here's the hash join algorithm. And remember, we have the partition phase, and then we have the build and probe phase that we go through for each pair of partitions. So partition S first, for each tuple T sub S and S. We go ahead and hash everything, and then write the tuples to the corresponding partitions. Then we do that for R, and then we start performing our hash join. Why do I do it in that order? I think it's like really dumb to do it in that order. Does anybody see why it would be dumb to do it in this order? Like, what's the first thing I do in the actual hash join proper? I read HSI first, right? So if I did this in the order that I partitioned R first and then partitioned S, then I could keep HS0 in memory, perhaps, and then use it, or maybe some blocks of it would already be cached, and I could leverage that to reduce IOs. So let me see. Maybe I explain in a subsequent. Yeah, so S is oh yeah, so optimization. Let's see. That just doesn't make sense to me. Why would I do that? Okay, let me see. I'll explain this maybe. So partitioning of R, tuples at hash. Oh yeah, so that's very clever. Yeah, what is this called? I think this is the hybrid hash join, right? Yeah, hybrid hash join. I'm sorry, I forgot what my slide said. So there are various versions of hash join that try to take this general approach and modify it in various ways. I forgot that this was for hybrid hash join, which I'm sorry, I should have remembered that. So I partition S, and as I'm doing it, I keep HS0 in memory. And then when I'm partitioning R, anything that goes into HR0, I don't actually create that partition. I just test it against HS0 as I'm going through it. So that's the reason why S is partitioned first. I apologize. I should have remembered that. Okay. Most of the hash join implementations that you'll see in databases are actually hybrid hash joins because it allows you to not have to keep HR0 around or even generate it. Because you can generate the joins from HR0 by keeping HS0 in memory as you go. Okay? Again, I apologize for forgetting about that. Any questions? Does that make sense to everybody, why we would do it this way? Okay. Let's see, outer joins with hash join. Well, we already talked about this, right? When we're in our probe phase, so we already built the index against the build relation, which is HSI. In this case, we have our in-memory hash index, and we are probing it. If we have a probe and it doesn't match anything, well then it's really easy to do left outer join. Okay. If TR has matching tuples, then I go ahead and generate the join results. Otherwise, I just pad nulls and out the door. Okay. Now what about, what should I ask? Right outer joins? Can we do right outer joins? Can somebody suggest a way to do right outer joins with this? Remember, I have all the tuples in HSI already in memory. There's a simple little technique or a simple little trick I can do, a little change I can make that will allow me to do right outer joins with this technique. How do I know when I need to generate a right outer joins tuple? Like, how would I know that a tuple in HSI needs to be output as a right outer join? Well, HSI is already in memory, so it's in there. There's actually a simpler way. Yeah.
I feel like there are stuff in one of the memory, and then when you're done adding stuff, you just go over and see kind of mark.
Yeah. Well, where would I store these marks? There's a really obvious place to store these marks. What about my in-memory hash index? If I just tweak it a little bit to know what's been hit when I do my probe, like this got probed, so everybody's got a probe flag now. And so if something never got hit during the probe phase, I know there's no tuples in HRI that match those tuples in HSI. And so I can do something very simple like that, where basically my hash index entries keep track of what actually matched stuff. And then what I can do is scan through the index and see what didn't match anything. So there's a very simple way of tweaking this to do right outer joins. A little bit less efficient than doing left outer joins, but it'll work. And so if I can do left outer joins and right outer joins, then I can also do full outer joins. Okay? Full outer join. So like I say here, you need to alter the hash index to record which tuples in this HSI were joined, because then I can know which tuples were not actually joined. Does everybody understand what I'm talking about here? I'm not talking about changing how HSI is loaded into memory, because that stays fixed. It's a tuple file, I load it, and I have like page tuples or something like that into HSI. It's all in that in-memory hash index. I can make all my tweaks there, because that's an in-memory data structure that I use to facilitate the join. Everybody got that? All right. What else do I want to say here? Obviously, if you can do left outer joins, you can do semi-joins and anti-joins. Hopefully everybody's got that by now. If I can do left outer joins, I can do semi-joins, because semi-joins mean I match something, and if I can do left outer joins, then I can also do anti-joins. All right. Let's see. So are there any questions about these other join algorithms? Oh, wow. We actually used up quite a bit of time. What I'll do next is go ahead and introduce the next topic. Okay, we had this query. Remember, select star from T1, T2, where we have, hey, an equijoin. We now have several ways of doing this. And T2.B is greater than 5. These are 3 plans that we could use. And I think I actually had that before and asked you guys, do you think they're equivalent or not? And we all agreed that they look equivalent, so we're okay. And you can imagine different situations where different ones would be helpful. Like the rightmost one might be really nice if there's an index on T2.B, but then maybe it constrains how we can evaluate the theta join, like we can't use a sort merge anymore if we also had an index on A, so maybe we'd actually prefer the middle plan and evaluate the B greater than 5 up above. We don't know, so we have to figure that stuff out. How do we know which plan is best? Given our schema and our data, of course. How do we know that the plans are actually equivalent? We're going to start talking about both of these questions in the next couple of lectures. And so we introduced the notion of plan costing. We've already talked about how much does a join cost in disk IOs, disk seeks, that kind of thing. There can be a lot of different ways of measuring plan cost. So like I say, your number of rows generated by each plan node, that actually turns out to be very, very important. And the number of disk accesses performed by each plan node. And then we could start getting more intelligent and saying, well, but I have to do a lot of CPU computation, and that's going to be slow. or I require a lot of memory. Sort merge needs memory to be happy, so I need to figure out if I can do this in a concurrent evaluation situation. Average size of each row in bytes. Why would that be important? Well, if I'm doing a distributed database system, I need to know how much data am I sending across the network or through shared memory to another database engine. So I'd have to think about that as well. So yeah, like I say here, T2 is a heap file with no indexes on B. How many disk blocks are accessed? So how many disk blocks would be accessed? Should be pretty obvious, right? Even if I only have like 10 rows where B is greater than 5, I still have to look at all the rows in T2. So I still access all the blocks in T2. How many rows will be produced? Well, do we have enough information to answer this question yet? The answer to this one is no, not yet. So here's a funny thing. If we knew the minimum and maximum values of B, we could make a guess as to how many rows we would produce here. The number of rows in T2 times this fraction. B max minus 5 over B max minus B min. It's a horrible estimate. But we can use this to generate more intelligent plans. It's funny. It's so horrible as a guess, but it'll work. Now, if we had a histogram, it's like maybe 1 through 4 is all of the values in T2.B, and then there's like 6 things that have B greater than 5. And if we had a histogram, then we could make a much better estimate of how many rows we might produce. So you can see that we need statistics. Yeah, is this a quick question? Because we're...
Can we store things like min and max as we insert people's episode?
We could, yeah. We'll talk about how we collect statistics in the next lecture. I don't want to get into that right now because we're already over time. But yeah, that's a good thing to think about. You'll actually get to implement this. Yeah, so stats are expensive because, especially things like min and max, we need to look at all the rows. And so databases have various ways of doing this. The one problem, of course, is if the stats differ widely from the actual data, our estimates are going to be terrible, and that means our plans are going to be terrible. So I think what I'm going to do, I wish I had this. I'm going to basically jump ahead, and we'll talk about that next time. But this is really what I want to focus on. Our costing estimates should be as accurate as possible, if we can. They should be easy to compute, logically consistent. Okay, we'll talk about this next time. But the reality is that it's not that good. And so all we really care about is that faster plans end up with lower costs than slow plans. If they do, then we'll generally choose the faster plans when we generate our options and we cost them. That's really our goal here, is that we want to end up with faster plans having lower costs than slower plans, no matter how good or bad the estimates in between are. Okay, are there any questions? We will talk about this more next time and get into